Hey everyone, Mr. Anderson one more time, coming to you today to talk about section 8.1.5 from our CPM Common Core ebook. And we're really going to investigate the question today and try to answer the question, is there a shortcut? Is there a way to expedite some of these factoring processes? And the answer to that is yes, there is a shortcut. There is a way to speed things up. If you know the type of pattern that you are looking for. I've thrown together some notes from what we have in our ebook here. We've got a couple problems, and we're going to use some of these problems to do some investigating. And if you're in person, your teacher may have a slightly different option for you in class that may or may not be a good one. So hopefully, if like I said, if you're in person and you are running through some of these things with your teacher in class, you've seen some of these things before. But first and foremost, we've got to know what kind of pattern we're looking for. And there's two that we really identify here. The first is what we call a difference of squares pattern. And I'm going to draw your attention to the fact that this is a binomial. And that means that our quadratic in this case is going to have two terms. Now I say quadratic. In other courses, that's because we only focus on quadratics in our algebra course. In other courses, it might not be a quadratic. It could be a higher degree function. And they may display some of these kinds of patterns. So don't let my language limit some of your thinking, okay? But we're going to have a binomial, and it could be a difference of squares pattern if, and this is my generalization here, if our coefficient on the x is a perfect square, if our x is a perfect square, if we have a subtraction difference, right? And then our constant term is a perfect square, right? All of those qualifications need to be met. And if we have that, we have a difference of squares pattern, and we can factor it using a reasonably quick shortcut. And I'll show you what one of those looks like here in problem letter A. So real quick, I'm just going to copy down A. I've got 25x squared minus 1. Now check this out. I've got 25, that's a perfect square because 5 squared is 25. My x is squared, right? That's also a perfect square. They are the constant and the x squared term are being subtracted, right? So that's important. It's a difference. And then, of course, we don't often recall this, right? So let me help you. 1 is a perfect square because 1 times 1 is 1. Okay. So what does this look like? Let me go the long way and factor this the way that we've done it, okay, many times in class and in prior videos, where we put our x squared term here, and we put our our constant term here, and and I forgot the square. There we go. And we go through this, and we start to rehearse. Okay, like my diagonal. If I'm going to multiply these two things, okay, 25x squared times -1. That's negative 25x squared. Okay, so I need these two things. I need factors of those that add up to 0, but also multiply to be negative 25x squared. And so we start that thinking that way. And I know factors are 5x and 5x. Okay, now how can I use that information? Okay, factors of 1. Well, there's only 2. There's 1 and 1. 1's got to be negative. Now, let's check this out. Does this work? This is negative 5x. This is positive 5x. Okay, so yeah, that's gonna work out really nicely because they multiply to be negative 25x squared, and of course they cancel each other out. That's the other thing that maybe we should draw our attention to here. There is 0x there. There's no middle term. Okay, so that middle term is effectively dropped out. That's why we have a binomial. But what's happened here? We've got this factored into the form 5x plus 1 and 5x minus 1. Now look at that, okay, because those two binomials in factored form looked almost identical. The only difference is one has a addition between the two terms, one has a subtraction between the two terms. And so if you look at that binomial perfect square pattern and you can say, oh, well, gee, I recognize the pattern, that is going to save you some time. Maybe you could eliminate doing this box work, okay? not every one of these is going to fit that term. So we're going to go ahead and just acknowledge that we do have to be cognizant of that. We do have to do some checking, but it certainly could save us some time, right? What if I moved on to something like letter E, this one right here, right? It's definitely a binomial, right? I've got a 9x squared, right? 9 is a perfect square. My x is a perfect square. Shoot, even this 4 is a perfect square because 2 times 2 is 4. Well, what's the issue here? Well, is that a difference? Well, in this particular case, this thing right here is not going to be factorable. At least not using any of the methods that we have right now at our disposal. Okay? So E in this case is not going to be factorable. And again, you're looking at that and you're going, but Anderson, like 3x times 3x is 9x squared and 2 times 2 is 4. And I agree wholeheartedly. The problem here is we don't have a difference in this binomial. All right? There's one other one we will look at, and that is factorable, and it's going to be over here. It's going to be letter F. And how to approach this one? Well, 9 is a perfect square, x squared is a perfect square. I do have a difference, and 100 is a perfect square. So this one is going to be factorable, right? And if you want to race me on this one, you definitely can. But let's go ahead and try to remember that pattern to save ourselves a little bit of time. Okay? I'm pausing for effect in case you're writing down in front of me here. What are the square roots of 9x squared and 100? Okay, they are 3x and 3x, right? And they are 10 and 10. And again, this is only because it's a difference of squares pattern. Now there's only one other thing I need. I need one of them to be completed with an addition, the other one to be completed with a subtraction. Now I got this factored. Okay, and that is my shortcut. All right, but it's only a functional thing when I have that working out in a difference of squares pattern. So I have to look for that first. All right, I'll back out and you guys can see A, E, and F there. All right. The other one I'm going to jump to or show to you guys today is what's called a perfect square trinomial. Now, I draw your attention to this word. It is a trinomial. It's trinomial because it is a, what's it called? A three-term polynomial. Okay? So I've got an x squared term, I've got an x term, and I've got a constant term. And there's some conditions here. All right? Just like before, my coefficient on my x squared term needs to be a perfect square. My x needs to be a perfect square. My constant term needs to be a perfect square. But now we've got this situation here where my x term needs to be twice the value of my a and b. And that seems confusing, but I hope to clear it up with an example. Okay? And I've got a slash here, and I've got something that looks almost identical here. The only difference is because we know a negative times a negative, it gives me a positive, I've got an option where we can subtract that middle term as well. Okay, and I'll show you both of these things because they do work out, I think, pretty gosh darn nicely. Okay, I'm going to start with something like letter C. Letter C looks like this. It is x squared plus 8x plus 16. And we'll do this one in blue because, you know, why not? I'm just going to rewrite down here, x squared, 8x, and 16. Now let's go ahead and look at this thing. And I'm going to factor it the way that we factored these things in the past. Okay, I've got my box, I've got my x squared term going right here, I've got my 16 term going right there. Now, it's really, of course, a very nice and convenient thing when you've got x squared because the only factors of x squared are x and x. So hopefully you're writing those reasonably quickly. But now we need to recognize, okay, I gotta, let's see, I gotta do that. Let's see, 16 times x squared, that's 16x squared. So I need, when I drop in some factors in there, they need to add to 8 and they need to multiply to be 16x squared. Well, one of the things I'm thinking right away is 2x and 8x for sure multiplies to be 16x squared, but it does not add up to 8. So let's see, there's got to be another factor pair. Let's see, what else? Oh, 4 and 4 multiplies to be 16. And conveniently, 4x and 4x multiplies to be 16x squared, and 4x adds up to be 8x. Okay, so another way of thinking here is if I multiply x, I need a 4 here to make that 4x, and if I multiply by x, I need a 4 here to make that 4x as well. Okay, now check this out, because look at this pattern. What do you notice? What do you notice there? They're the exact same, right? And sometimes we even write these like this, right? Repeated multiplication. So what's the takeaway, right? It's an x squared, and in case you don't remember, right, there is a perfect square out there. It's 1. This is a squared term, right? 4 times 4 is 16, and this is twice a and b, right? The square root of 1 is 1. The square root of 16 is 4. 1 times 4 is 4, and twice that is 8. Okay? So that could save you a little bit of time as well. Let's go ahead and knock out one more of these guys as well. And the one I'm going to choose to do here is going to be letter D. And we're going to do letter D right down here in green. It is 9x squared minus 12x plus 4. Okay? And we're going to use the pattern on this particular one to tackle it, right? And I'm pausing, I'm taking a drink of coffee here because maybe you are going to try to tackle that one on your own first, right? Maybe you should pause the video and try to tackle that one on your own. Do you recognize the shortcut, right? Here's what I'm thinking. I'm just going to kind of do my thinking here. 9 is a perfect square because I know that 3 times 3 is 9, right? 4 is a perfect square because I know that 2 times 2 is 4. Okay? So the question then is, I've got a trinomial. What is 3 times 2? Well, 3 times 2 is 6, and twice that. Isn't it true that 2 times 3 times 2 is 12? And it sure is. Okay, now we've got to do a little bit of work here to make this work out because it's there's something, maybe you saw it here, that's going to maybe complicate our work here, but it's not too bad, I promise. I'm going to go ahead and just write this as a product of two binomials. I've got my 3x, I've got my 3x, I've got my 2 and my 2. All right. And then, ladies and gentlemen, because that b term, because that 12x is negative, these are going to be negative as well. All right. And that maybe saves you a little bit of time. And just like the other one, of course, I could do this, right? Some of you might be screaming at your computer screens there. I could do that as well. Both would be fine. And that was letter D. All right, real quick, let me back up. Let me examine something like letter B, and let's just talk about the elephant in the room on this one. Yeah, this is definitely 1x times 1x. That's a perfect square. This is definitely 6 times 6. The problem we're going to run into here is that this is not going to be factorable using one of these special patterns because this is not double 1x times 6, right? It's not twice that. It's not 6 and 1 make 12, 6 and 1 make 6, and double that is 12, right? It's not 12x, right? The other thing is, I don't know if any of you caught this in our patterning, but that would have to be a positive constant term, okay? So there's a couple of like quick factoring patterns for you guys, and there is that written like very, very formally, and I encourage you guys to read problem 8-47 because they outline these patterns, and I tried to do a little example, a couple of examples, rather than just go with some of the formal language they have written. But some of you will be here and you'll be ready for this. Some of you are going to say, Anderson, this is hogwash and malarkey, and why can't I just use the generic rectangle to do some factoring? Because I'm fine with that. And the answer to that question is you definitely can. All right, the generic rectangle will still work 100% of the time for us. This is just a shortcut when and if you are ready for it. Okay, a little bit of review preview here. It is 49 to 52. I want you trying these things to make sure we get all those questions asked and answered. Ladies and gentlemen, I appreciate your time. Thanks for watching. Have a great day.